Welcome to This Explainer. I'm absolutely thrilled to have you here today. If you're a focused learner looking to unlock the real secrets of physical chemistry, well, you've landed in exactly the right place. Today, we're going to tackle one of the most notoriously intimidating concepts in all of science. But don't worry, we're doing it logically, cleanly, and through the power of structured understanding. We are going to demystify the mole concept.
I want you to really think about this for a second. How on earth do you count something you can't even see? It sounds completely absurd, right? But honestly, that is the fundamental challenge of physical chemistry. It's essentially mathematics applied to matter. We are literally trying to quantify the invisible. And to do that, we got to start at the absolute foundation of matter itself. And that foundation is, of course, the atom. The word actually comes from the Greek atomos, which means indivisible. Now, roughly 200 years ago, a researcher named John Dalton proposed that everything in the universe is made of these atoms. Think of them like the bricks of a building, just like how different arrangements of the exact same bricks can create incredibly different structures, from a tiny house to a massive skyscraper. Different arrangements of these fundamental particles create literally every element and molecule in existence.
But science is all about evolution, right? Let's move through this and see how it builds. While Dalton originally envisioned a solid, indivisible sphere, a deeper pattern emerged over time. By the 1850s, we discovered electrons. Then came protons and later neutrons. Today, if we look even further inside the nucleus, we find quarks, which physicists sometimes jokingly call quacks. And, according to string theory, inside those are tiny vibrating strings. Now, while quark research is still very much ongoing, for our foundational calculations today, we really only need to worry about the big three: electrons, protons, and neutrons. Now, here is where standard math just completely fails us in the laboratory. A single proton weighs approximately 1.67 times 10 to the negative 24th grams. I mean, that is an unimaginably small weight. You obviously cannot put a single atom on a standard scale. So it becomes an absolutely impossible counting problem if you try to work with just one particle at a time. What's really fascinating here is how these tiny particles dictate the absolute rules of chemistry. The proton is the ultimate defining parameter. It never, ever changes for a given element. If you change the proton count, you literally change the element itself. Electrons, on the other hand, can be gained or lost to create negatively or positively charged ions. And neutrons? Well, they can vary to create isotopes, like heavy radioactive forms of hydrogen, which actually proved Dalton's early idea that all atoms of an element are perfectly identical to be totally wrong. Look, if you're feeling slightly intimidated by all these moving parts right now, validate that feeling. It is completely normal. As one of the foundational notes for our explainer states, in organic chemistry, in 10 minutes you can solve any question. In physical chemistry, you need to think for 10 minutes just to get the foundation. Unlike inorganic chemistry, which heavily relies on memorizing facts and reactions, physical chemistry requires deep, logical understanding. You simply can't just memorize your way out of it. But hey, don't worry, because scientists realized this microscopic counting problem was driving them crazy too. They desperately needed a bridge between the invisible world of atoms and the visible world of scales and beakers in the lab. So, enter our hero, the mole concept. This is the brilliant, elegant solution designed to fix this exact impossible problem. Let's forget the complex math for a second. Think about this. When you go to the store and ask for a dozen eggs, you know you're getting 12. If you buy a pair of shoes, you know you're getting 2. Well, a mole is exactly the same thing. It's just a grouping word. It just happens to be a grouping word for a very, very large number. If you have half a mole, it works exactly the same way as having half a dozen.
And that specific number is Avogadro's number, 6.022 times 10 to the 23rd power. If you have 1 mole of carbon atoms, you have 6.022 times 10 to the 23rd carbon atoms. If you have a mole of water molecules, you have that exact massive number of water molecules. It is a huge quantity, but it was chosen for a very specific, almost magical reason.
So the absolutely crucial point here is why Avogadro's number is so specifically 6.022 times 10 to the 23rd. It was carefully chosen so that the mass of one single atom in atomic mass units perfectly matches the mass of 1 mole of those atoms in grams. Think of it as a mathematical magic trick. A single carbon atom weighs 12 AMU. Because of Avogadro's number, 1 mole of carbon atoms perfectly, cleanly weighs exactly 12 grams. That reciprocal cancellation makes unit conversion beautifully clean. And this right here is what we call molar mass. Now that we finally have our bridge between invisible atoms and physical grams, we can use a highly practical tool, the conversion triangle. Think of the conversion triangle kind of like a universal currency exchange booth at an airport. You're just exchanging the currency of the invisible atomic world into the physical currency of the lab. Whenever you're faced with a calculation, always just start from the currency you have and follow the path. Let's trace the forward path first. If you're standing in a lab physically holding a chunk of material, you have its weight in grams. To exchange that into the language of the atomic world, your first step is to divide by its molar mass. That gets you moles. Okay, you've made the exchange. Then, step 2, to find out exactly how many individual invisible particles are sitting there in your hand, you take those moles and simply multiply by Avogadro's number. And the really beautiful thing is, this exchange booth works seamlessly in reverse. If a problem gives you an impossible, massive number of particles, you divide by Avogadro's number to group them into manageable moles. Then, for step 2, you multiply those moles by the molar mass, and boom, you instantly know exactly how many grams that huge pile of microscopic particles will weigh on a real-world scale. Okay, let's dive into this with a concrete example to prove how effortless this can really be. Let's look at sodium, represented by the symbol Na. If you check the periodic table, the atomic mass of a single sodium atom is 23 AMU. Applying our magic trick rule, that means the molar mass is 23 grams per mole. The result, if you need exactly 1 mole of sodium for an experiment, you literally just weigh out exactly 23 grams. Easy, right? All right, let's try something slightly more advanced using our conversion logic, finding the exact number of electrons in half a mole of an iron ion. A neutral iron atom, Fe, has an atomic number of 26, meaning it normally has 26 electrons. But this is Fe2+, a positive ion, which means it lost 2 electrons. So every single ion here has 24 electrons. If we have 0.5 moles of this ion, we just multiply that 0.5 times the 24 electrons per ion times Avogadro's number. And just like that, without breaking a sweat, you've counted the exact number of subatomic particles in a sample. Now, at this point, you might be sitting there thinking, okay, this triangle is a neat trick, but why does all this math actually matter? And that is a great question. Why do we spend so much time grouping and counting invisible things? Well, let's zoom out from the microscopic scale for a second and look at the broader implications. On a highly strategic and practical level, for students, mastering this foundation is incredibly vital. In competitive engineering exams, like the JEE Mains and Advanced in India, for example, physical chemistry makes up roughly 40 to 45% of the chemistry paper. The JEE Advanced, which is required for the prestigious IITs, actually changes its dynamic format every year specifically to test this kind of deep, conceptual application. But even beyond exams, math is the fundamental language of all science. Literally every discipline, from biology to astrophysics, uses mathematical patterns to express laws and predict the future. In fact, if we look at the entire composition of the universe, mathematical calculation is exactly how we discover things we can't even see. The universe is approximately 63% dark matter. And get this, we have never directly observed dark matter. Just like antimatter or the Higgs boson, its existence was completely inferred mathematically from calculation discrepancies. By doing the math on the observable matter, scientists realized that something absolutely massive was missing. And when we calculate mass on an atomic level perfectly, we unlock the very power of the universe. Consider Einstein's famous relativistic physics equation, E equals mc squared. Mass can literally convert to energy. In nuclear fission, when a heavy atom splits, a tiny bit of mass actually goes missing. This is called a mass defect, and it is instantly converted into massive amounts of energy. This is exactly why the specific isotope U-235 is used in nuclear reactors. It has a greater mass defect than U-238. Back when Oppenheimer was calculating high-stakes chain reactions, calculating this mass accurately was quite literally a matter of life and death. If miscalculated by even a tiny margin, the exponential chain could completely collapse, or worse, explode uncontrollably. We've seen how these microscopic calculations trace all the way back to a single point of infinite density in the Big Bang, and how they actually shaped the very conditions of human evolution. So I'm going to leave you with this provocative thought as we wrap up this explainer. If we can accurately count invisible atoms using just a simple conversion triangle, what other universe-defining patterns are out there just waiting to be observed and calculated by you?